Hello viewers. So, now let us go ahead with this subject of gravitational waves, which is nothing but we can say it is sound of gravity. We discussed that how special relativity forbids anything to move faster than the speed of light, and therefore, we can say that since general relativity is a theory of gravity that is consistent with special relativity, it also should say no gravitational effects should propagate faster than the speed of light. So, imagine that you have a very massive object and there is another lighter object which is going around in an elliptical orbit around the massive object. So, supposing I am standing here, what do I see? Newton's gravity will tell me that because although the distance of this object is fixed with respect to me, but this object the distance is changing periodically, and therefore, Newton's gravity will say that I should be instantaneously seeing the changing gravitational field at this point, due to the fact this lighter mass is moving around the bigger part. But we know that such a thing cannot be instantaneous, because special relativity forbids us, and general theory of relativity, which is a theory of gravity that is consistent with special theory of relativity, tells me that if this moves, the change in its gravity can at the most propagate towards me with speed of light, and this change of gravity propagating outward with speed of light is what manifests as gravitational waves. So, in other words, because general theory of relativity is a relativistic theory of gravity, any change of matter distribution that is sufficiently asymmetric, the changing gravity propagates outwards like a wave, and that is what we call gravitational wave. But also I mentioned that truly speaking, gravity is not a force at all, but gravity according to general relativity is a manifestation of non-Euclidean nature of geometry. So, in other words, when an object, its matter distribution changes with time, the change in the space time geometry itself propagates outside like a ripple. So, therefore, gravitational waves is nothing but a ripple in the space time geometry. So, imagine that if you had two masses, both had identical mass m, one mass was having a charge q and the other charge minus q, and let us say we connect these two masses by a spring. If we set this system in oscillation, then Maxwell's electrodynamics tells me that because the electric dipole moment is changing periodically with time, such an object will send out an electromagnetic wave. But Einstein's general relativity also tells me that because these carry masses and the change in mass is asymmetric, there is no spherical symmetry, and therefore, as the mass distribution changes because of the oscillation, it sends out a changing gravitational field, which is called gravitational wave. Or another way of looking at it is the geometry of the space time itself will be changing, but that the change will be moving out in the form of a wave. The true mathematical connection between the changing matter distribution and the amplitude of the change in the geometry is given by this equation, where Hij is the perturbation in the geometry of the space time, and capital I is some kind of a moment of inertia for this object. And what this quadrupole formula tells you is the geometrical fluctuation of the space time is equal to twice Newton's gravitational constant divided by distance to the source where all this is happening, multiplied by fourth power of the speed of light, and the whole thing is multiplied to second order time derivative of some kind of a moment of inertia of the matter distribution. That means the matter must change with time, because there are these two derivatives with respect to time. Only then it will cause ripples in the space time geometry. But note one thing, in front of the second derivative of the moment of inertia tensor, there is this factor g divided by distance multiplied by 4th power of c. The value of Newton's constant in CGS unit is only 6.67 into 10 to the power minus 8, while speed of light in CGS unit is 3 into 10 to the power 10 centimeters per second, but 4th power is a huge number. The distance to an astrophysical source, this r, is also a huge number, more than tens of light years. So, this number g divided by r into c raised to power 4 is a very, very tiny number. No matter how big is the mass, this entire quantity is expected to be very, very tiny, and that is precisely the reason why it took 100 years to measure this gravitational wave amplitude Hij. Although it was predicted 100 years back, but this number is very, very tiny. To give an example, supposing there is a supernova, which is a exploding star which goes off around 10,000 or 30,000 light years away from Earth. Supernova is a huge mass blasting off, then the amplitude of the gravitational wave, that means the fluctuation in the space time geometry denoted by Hij, will be so tiny that, because it is a changing geometry, if I have some two mirrors which are separated by 4 kilometers, if these two mirrors, when the gravitational wave passes by, because this amplitude is change of geometry, and what does geometry do? Geometry tells us how to compute distances and angles, and now as the gravitational wave passes by, the geometry is no longer Euclidean. The change in the distance because of the changing geometry, if the two mirrors are kept 4 kilometers away from each other, the change in the distance now due to this gravitational wave will be 1,000th of the diameter of the proton. You all know diameter of a proton is about 1 Fermi. What is 1 Fermi? 1 Fermi is 10 raised to the power minus 15 meters, and a gravitational wave from such a powerful source like supernova, the change it will cause over the 4 kilometer separation is 1,000th of the diameter of the proton. How the hell are we going to measure this? That was the challenge for 100 years, and what LIGO detectors have shown is that one can do it. Of course, the event had much bigger masses, not like one supernova. That is why this signal was slightly stronger. I will talk about it in the course of this lecture. Two few things I want to mention. One is, just like electromagnetic waves have two polarization. So, you can have electric field moving up and down in the y axis when the wave is passing in the x direction, that is one linear polarization, or as the wave is moving in the x direction, the electric field can move up and down in the z direction, that is the orthogonal polarization. Gravitational wave has also two polarization, but the slightly different. So, supposing you have a ring of test particle, one polarization what we will do is, when gravitational wave passes into the system, the test particle initially the distance will get out stretched out, they will get stretched out, then again contract. After some time the vertically they will be stretched out, while the other polarization, if it goes through, then in a 45 degrees initially they will get stretched out. In the next half cycle of the wave, this part will get stretched out, this part will get compressed. So, although there are two polarization, but unlike in the case of electromagnetic waves where the two distinct polarizations are perpendicular to each other, here the two distinct polarizations are 45 degrees angles apart. Sources of gravitational wave, as I said, one would be supernova explosion. This is the Crab nebula, which was the Crab stars exploding in 1054 AD. How do we know that? Because Chinese astronomers indeed recorded such an explosion in 1054 AD. Or you could have a star with some asymmetry rotating about, or you have binary stars going about the common center of mass. In all these cases, the mass distribution is changing asymmetrically, and they would lead to change in the geometry. Similarly, another very common source which is envisaged is two merging neutron stars. Neutron stars are very compact stars which are essentially made of neutrons. So, if you want to turn our sun into a neutron star, you have to compress the sun to a radius of 10 kilometers. Then at such high densities, inverse beta decay will make proton and electron go into neutrons and neutrinos will escape. So, that a compressed sun to a radius of only 10 kilometers will essentially become neutron rich. And we also know most of the stars, 50% of the stars in our galaxy, they are not single stars, they are binary stars, they are going about the common center of mass. And if you have two such neutron stars going around each other, they will radiate out gravitational waves, but because gravitational waves carry energy, this binary system will lose energy. Because energy is getting lost, the neutron stars, their distance between them keep on shrinking. Because the distance between them keeps on shrinking, they will go faster and faster, and they will keep on emitting more and more gravitational waves. Finally, they merge, and when they touch and merge, intense gamma radiation is emitted, and also gravitational wave. Such gamma radiation are what are believed to power gamma ray bursts. So, we believe that such gamma ray bursts will also be intense source of gravitational wave radiation. Why did I talk about the two neutron stars as a source of gravitational wave? The reason is that in 1974, two astronomers, Taylor and his student Hulse, they discovered two neutron stars which are going around the common center of mass. Neutron stars are visible to us, some of them as pulsars, because the neutron stars, if you have this as a neutron star rotating about this axis, they rotate very fast, but their magnetic field, they are inclined with respect to the rotation axis. So, when the magnetic field lines are changing with respect to me, that means changing magnetic field will give rise to electric field. These electric field will accelerate charged particles, and these charged particles will move along strong magnetic fields, radiating intense radiation, and we will see as pulses of radiation. And Hulse and Taylor, they discovered a binary pulsar where the two pulsars are going around each other, and pulses from one pulsar was visible to the earth. And by noting how the pulses are getting modulated as they move about. Why would they get modulated? Because if to a earth based astronomer this pulsar is rotating, then due to Doppler shift, the period of the pulses will keep on changing. So, by measuring the change in the period of the pulses, you can estimate how the orbit is evolving for the pulsar as it goes around the common center of mass. By monitoring for many years from 1974 onwards, how the period of the pulsar, the orbital period is shrinking, because if they emit gravitational waves, then they will come close by and the orbital period will become smaller and smaller. They found that it is doing exactly what they should do according to Einstein-Landau-Lifshitz formula of radiation of gravitational waves. Einstein, Landau and Lifshitz had worked out a formula by which you could calculate amount of energy carried away by gravitational waves, and Hulse and Taylor found out that these pulsars were coming towards each other because they are losing energy in the form of gravitational waves, and that loss of energy rate exactly matches with the Einstein-Landau-Lifshitz formula. They did not detect gravitational waves. What they showed was the theoretical formula calculated by Einstein, Landau and Lifshitz predicts the right rate at which energy should get lost from this binary pulsar, and therefore, Hulse-Taylor binary pulsar gave an indirect confirmation of the theoretical gravitational wave calculations, and because of which in 1993 both of them were awarded the Nobel Prize. But it was not a direct detection, because no one detected the gravitational wave amplitude, or which is the fluctuation in the space time geometry. What was detected was recently, that is on 14th September 2015, and that was due to two black holes which are going around by the about their common center of mass. What are black holes? Black holes have a mathematical surface called the event horizon, from which nothing can escape, and therefore, this mathematical surface can never be seen. It is completely black. In other words, if you want to convert sun into black hole, sun has a mass which is 2 into 10 to the power 33 grams, but its present radius is about 7 times 10 to the power 10 centimeters. That means 7 times 10 to the power 5 kilometers. If you want to convert the sun into black hole, it can't naturally become black hole, but if you wish to convert our sun into a black hole, what you have to do is compress the sun to a radius less than 3 kilometers. Then sun will collapse to a single point. That means what? Entire mass 2 into 10 to the power 33 gram will get concentrated a single point, that means density will become infinity. Whenever infinities appear in physics, we call they are singularities. So, black hole is singular solution, because the density at this point is infinite, and general relativity says there the curvature of the space time geometry also becomes infinite. Why did I use the word 3 kilometers? Because 3 kilometer happens to be the Schwarzschild radius for sun. Schwarzschild showed in his solution that if you have a star of mass m, then the corresponding gravitational radius is twice g times mass divided by c square, where j is the Newton's gravitational constant, c is the speed of light. For sun, if you put in this formula 2 g m by c square, the mass m equal to 2 into 10 to the power 33 gram, you will get 3 kilometer radius. What general relativity showed was this mathematical surface, spherical surface at the Schwarzschild radius, which is today called the event horizon, is such that any event that happens below the event horizon, even light from such an event cannot cross the event horizon. That means, this surface hides everything that is happening beneath the surface. So, therefore, if you have a black hole, you can observe things only that is happening outside the event horizon, not that which happens inside. Now, if you have two black holes which are going around a common center of mass, the mass distribution goes on changing in an asymmetric fashion, and therefore, from that gravitational waves will emanate, ripples of the space time geometry will come out of it, and if you have powerful detectors, then you should be able to observe it. And what is the prediction? Theoretical prediction says that when the two stars go around coming close to each other, initially the gravitational wave amplitude, that Hij, initially the amplitude is small, they are almost the wavelength is same, but as they lose energy they come close to each other and the orbital frequency becomes faster and faster. So, the wavelength keeps on decreasing, the amplitude also goes up, because now the mass is changing at a much faster rate, because the orbital velocities have become fast, and eventually the wavelength becomes very tiny, the amplitude becomes very small, they merge forming a black hole, and a newly formed black hole, because it is a disturbed black hole, it rings like a bell, I will tell a little bit about it later on. So, in other words, if you have such a binary system, theoretical calculation tells that when the two stars are far away, then the wavelength is almost constant, but as they merge towards each other, the wavelength keeps on decreasing. Finally, they merge and can form a bigger black hole. So, here is a much bigger picture of this. So, initially when the two stars were far apart, the wavelength did not change much, but when they came close by, the wavelength kept on decreasing, very small it becomes, the amplitude becomes very high, formed a big black hole, and there is a ring down. Instead of the ring down phase, that means a disturbed black hole, it rings like a bell and the amplitude exponentially decays. This was actually first done by an Indian general relativist when he was a PhD student at the University of Maryland. His name is C.V. Vishweshwara. In fact, the event which was recorded last year in the month of September, that is consistent with Vishweshwaraya's prediction. And what has been concluded from the data, I will show you the actual data soon, but lot of computer data analysis goes on, and for the event that happened on 15th September 2015, what is known is that the two objects were black holes going around the common center of mass. One black hole was 29 times heavier than Sun, the other black hole was 36 times heavier than Sun, and within few seconds they coalesced to form a bigger black hole whose mass is 62 times heavier than Sun. You can immediately notice that 62 is not equal to 29 plus 36. Where is the additional 3 solar mass gone? It is E equal to mc square formula. It is that 3 solar mass which appears as gravitational waves. That means, the amount of energy carried away by the gravitational waves is 3 times the rest energy of the Sun. How much is it? If you do the calculation, you will find it is about 54 into 10 raised to the power 53 ergs. So, in about few seconds, the gravitational wave energy that was released is 54 times 10 raised to the power 53 ergs, and that sort of outshone all powerful sources in the universe, and this is the actual data. So, there were 2 detectors, 2 laser interferometer detectors, one at Hanford in Washington, the other at Livingston in Louisiana, and Louisiana first detected the so called chirp signal, but you can see it is highly noisy, not that beautiful theoretical curve, and 7 milliseconds later the Hanford detector saw it. Why a delay? I will talk about it more. Do a computer data analysis so that you remove the noise, and you find now after removing the noise, the signals are more like the theoretical calculation, and once you remove the noise from these actual observed data, you use the theoretical calculated model, try to extract the parameters, and that extracted parameter tells us one was 29 times heavier than Sun, the other was 36 times heavier than Sun. So, here is the United States of America, and you have the 2 detectors which are separated by about 3000 kilometers, and the detector from the top it looks like this. Here are the 2 arms of the laser interferometer, the other detector has this other 2 arms. As I said, the Louisiana detector first saw the event, and the Hanford, the Washington saw the event 7 milliseconds later. What it means, why should it happen? Because if a gravitational wave comes from a direction, the gravitational wave is almost coming like a plane wave, but if the direction is such that the plane wave first hits the Louisiana detector, then as the wave goes, then it hits the Washington detector, and therefore, there is a time delay. From the time delay you can work out, therefore, the gravitational wave source can be anywhere in a cone, centered cone making an angle 47 degree about this line joining the Hanford detector to the Livingstone detector. This event after the data analysis not only gave the first direct measurement of the gravitational wave amplitude, but for the first time we have almost a direct detection of massive black hole. So, again let me repeat, not only the event corroborated the existence of gravitational wave directly, but it also gave indirect detection of the existence of massive black holes. The reason is the masses 29 times heavier and 36 times heavier object, which are so compact because they came very close to each other from the high frequency or small wavelength. You can say how close they came to each other. That means the two stars must have been very compact in size. Such compact and heavy stars cannot exist in any other state but in the form of black holes. Not only that, as I said, it is consistent with the ringing mode of the black hole, perturbed black hole, which was predicted by C.V. Vishweshwara. I did a small calculation to show that these results are also consistent with a theorem proved by Stephen Hawking, which is called the black hole area theorem. According to Hawking's black hole area theorem, what it says is that if you take a black hole with a given event horizon, you can calculate the area of the event horizon. If the Schwarzschild radius is Rs for a spherically symmetric black hole, the event horizon area will be 4 pi Rs square. Then Hawking proved that no matter what you do to the black hole, whether you put in matter or you try to spin it or do whatever, at the level of classical general relativity, you cannot decrease the area of the event horizon. All classical processes can only increase the area of the event horizon. So, I did a calculation with the parameters which was reported in the paper which reported about this black hole, and showed that indeed the two black holes, when they coalesced and form a bigger black hole, the event horizon area of the bigger black hole, remember 3 solar mass was radiated away as gravitational wave. So, the total mass was not sum of the two masses, but the total area of the event horizon of the final black hole mass is bigger than the sum of the event horizon of the initial masses. So, therefore, it is consistent with Hawking's black hole area theorem. The other things that were confirmed is the so called chirp waveform, where I showed that the wavelength keeps on decreasing and the amplitude keeps on going up. Such a waveform is called a chirp because it is like the chirp of a bird, or like if you heard quails cooing, then you know in the beginning the wavelength is longer, the pitch is low, but towards the end the pitch is high. Many birds have that kind of a chirping sound. That is why this waveform is called chirp waveform, and the theoretical form of the chirp was confirmed by this experimental detection. Similarly, I have already mentioned the so called quasi normal mode oscillation of a perturbed black hole, which was predicted in 1970 by Vishweshwara, was also confirmed, and I have also mentioned that the energy, the 3 solar mass carried away by the gravitational wave was so bright that it was 50 times brighter than any other source in the universe that time, and the distance of the source is more than 400 megaparsec, which translates to a distance of about 1.3 billion light years away. Now, in the remaining 5 to 10 minutes, I will quickly summarize what all possible sources we have. We have already seen coalescing binary compact objects giving rise to gravitational wave. Then I have talked about pulsars. If you have a rotating neutron star, and if there is a hill on the rotating neutron star or any asymmetry, then because it is rotating and the asymmetrical rotation will send out periodic gravitational waves. Similarly, you can have a star which collapses when all the nuclear fuel gets exhausted, then the gravitational collapse will cause lot of neutrino emission, which will deposit their energy on the outer envelope of the star, causing a supernova explosion, and that explosion itself is likely to be asymmetric and show huge amount of gravitational wave. As we know, pulsars, this is an actual X-ray image of the crab pulsar. As you can see, the X-ray image itself hints about the rotation, and the pulsars rotate very fast. The crab pulsar, it is going around 360 degrees every 33 millisecond. Most pulsars are much faster rotating. You have also millisecond pulsars. So, with this fast rotation, if there is any asymmetry, it will produce huge amount of periodic gravitational waves. Then all kinds of stellar evolution can produce gravitational wave, like type 1a supernova, where if you have a white dwarf, if another star falls on the white dwarf or any matter falls on the white dwarf, once the mass of the white dwarf becomes greater than Chandrasekhar's critical mass, it has to collapse into compact object, and then neutrinos released will detonate the star into a supernova, and again gravitational waves will be released. Now, let me concentrate on what are the detectors which are used to detect gravitational wave, because for LIGO India, with cutting edge experiments which are going to soon come into India, it will be great excitement for our young students, because all kinds of fantastic experimental physics which so far has not yet come into India will come in, and experiments will be fantastically exciting. So, what is the basic idea behind the detection scheme? Remember, gravitational wave, we have said, is nothing but a fluctuating geometry. In other words, what does a fluctuating geometry do? Supposing I have a circle of test particles, small particles arranged in a circle, then as I have said that if the gravitational wave crosses this in a perpendicular direction, initially these particles, the distance between them will increase, while these particles, the distance will contract. But after a half cycle, what will happen is that, so they will get stretched out. After a half cycle, these will get stretched out, that means distance will increase, and these will get compressed. If that is the case, now it is very simple. All you do is that you want to measure the distances. So, you arrange, let us say first a simple Michelson interferometer. In a Michelson interferometer, what you have is a laser source, you have a beam splitter, you have two mirrors. So, the beam splitter will split the light beam, one will go into this arm, the other will go into the arm, get reflected, then finally they will get combined. Then depending upon the difference in the length of the arm, there will be constructive and destructive interference, and if you have a photodiode like detector here, then you will see fringes. There will be bright fringe where there is constructive interference, dark fringe where there is destructive interference, and so on. So, supposing you want to detect gravitational wave, what you will do is you create a situation, arrange the arm length in such a way that the light beam finally, when it comes out here, there is complete destructive interference. So, that means no light beam comes out, there is a dark spot. You might say, what about the conservation of energy? I sent in light, the energy must be conserved, the light has gone out. So, when they combine this part, there is no light, destructive interference, this part complete constructive interference, the light actually goes towards the laser. If you put a mirror here and form a cavity, the laser intrinsic radiation plus this radiation, you can recycle and create a powerful laser, and that is what is done. So, in the absence of gravitational wave, your photodiode is sitting in the dark spot, no current. Okay. Now, when a gravitational wave passes, one arm gets stretched, the other arm gets, in the first cycle, gets compressed. Now, there is a change in the length. So, no longer is a dark spot, there is an oscillation, dark will go to bright to dark to bright to dark. This oscillation, the intensity change will give you the signature of the gravitational wave, because the length is changing. And here is a picture of the LIGO detector, one arm here, the other arm in this direction. But in the real experiment, it is not a Michelson interferometer, rather it is a Fabry-Perot cavity. So, here is a laser beam splitter, you have two mirrors in one arm, two mirrors in the other arm. You actually store the light by putting them in a resonant cavity, and so in the absence of gravitational wave, the light is stored in the two arms. So, it is in a resonant cavity mode, and when the gravitational wave comes in, the resonance is disturbed and light leaks out and your photodetector detects it. And therefore, as we have shown that plus polarization, the ring of particles initially this will get stretched, then after some time this part will get stretched, while if you have a 45-degree away polarization, the rings will get stretched in a different direction and you can detect it using the Fabry-Perot cavity. Now, let me tell you what are the quantum things which are going to be used. You know that laser is really a coherent quantum light, but because of quantum uncertainty principle, the uncertainty in the number of photons into uncertainty in the phase of the laser light is equal to, can be only greater than or equal to 1. So, if this is the number of photon and phase, then you do not know number of photon and the phase in a ball, because delta n into delta phi at the least can be only 1. But you want to measure phase changes very well, because you see 10⁻³ of the proton diameter, which is a tiny amount, that causes a very tiny change in the phase. If you want to measure phase changes, your phase measurement accuracy must be very small. So, this will not do. What you have to do is you choose two different parameters using squeeze state of light, so that uncertainty in the phase, this direction is the phase, this direction is the number, uncertainty in the phase can be squeezed. You do not care whether the uncertainty in the number of photons become larger. So, using squeeze states you will be able to see much weaker gravitational wave, and so far in India no one does experiments with squeeze states of light. So, when LIGO India comes up, that is what we are going to do. We are going to use squeeze state of light. Just the last thing, although laser interferometers are going to be the most popular measurement devices to detect gravitational waves, but we must not forget that the first detector for gravitational waves was given by Weber, who is no more. Weber was the first person in 1960s. He constructed a huge aluminum bar detector. If there is a gravitational wave whose frequency exactly resonates with the natural frequency of the bar, then the bar will oscillate and you will be able to detect the oscillation. He also claimed that he detected something. Unfortunately, it was incorrect, but nevertheless we must give credit to Weber for being courageous to produce such a fantastic resonant detector, because only that showed that what you could do with better detectors like laser interferometric detectors. And there is a future proposal to put a gravitational wave interferometer in the space in an orbit around the sun. So, it will be following Earth. So, supposing sun is in that direction, Earth is going around sun, moon is going around Earth. These three space based detectors will be placed in an equilateral triangle. Each of them will be going around sun, so that they maintain an equilateral triangle and they will be following Earth. Such a detector will be able to detect gravitational wave of very low frequency, so that you can detect supermassive black hole gravitational waves, including gravitational waves predicted from inflation and other things of cosmology. And eventually we will be able to know more about the universe using gravitational wave as an astronomical tool. Why? Because light has greater interaction, and therefore sun, for example, when you see the light, you see only from the surface, you do not see what is happening in the core, because core light gets scattered, it cannot emerge out, light interacts strongly. While if the core emits gravitational waves from the sun, it will be directly caught, because gravitational wave does not interact with matter. So, in principle, if you have space based gravitational wave detectors during Big Bang, the kind of gravitational wave created during Big Bang due to quantum fluctuation, their wavelength will be stretched due to expansion, and if you have a space based detector, we will be able to detect and we can directly see what are the quantum gravitational signatures of gravitational wave during the Big Bang, and we can answer the questions concerning the epoch when the entire space time and matter themselves were created during the epoch of Big Bang. Ultimately, human brain is the only brain that is capable of understanding the mysteries of nature, although it is made out of the same elements that make the entire universe. Thank you very much.